Hello, my name is Rob Lynch. Thank you for watching this presentation on calculating medical reserves for claims which have been incurred but not yet received or paid, commonly referred to as IBNR. This presentation is primarily targeted toward actuaries practicing in the field of healthcare financing and whose responsibilities include calculating IBNR reserves. I will go through this presentation in 5 parts. First, a brief introduction to IBNR calculation, followed by an examination of what I will call 2 traditional approaches for calculating IBNR, the completion factor and the Bornhueter-Ferguson methods. I will then present a step-by-step procedure for calculating point estimates of medical IBNR by the average PMPM lag method, followed by the process for calculating confidence intervals for those estimates. Finally, I will include brief conclusions and observations on the methodologies. The calculation process for medical IBNR by actuaries has for decades been dominated by 2 approaches, the completion factor method and to a lesser degree the Bornhueter-Ferguson method. I will demonstrate here that both of these methods are deeply flawed. I will present a direct alternative approach, the average PMPM lag method, which gives much better accuracy and allows for the direct calculation of confidence intervals for the point estimates. The completion factor method relies on the basic assumption that claims are paid at a constant rate, regardless of total volume. This assumption necessarily implies that claims paid in a given lag month L, that is paid L months after their incurral, are positively correlated with amounts paid in prior lag months. It is based on the following relationship: amounts paid in incurral month M, lag month L, divided by the sum of already paid amounts for month M, lag months 0 through L-1, equals the sum of amounts paid in lag months L for prior incurral months, divided by the sum of all paid amounts through incurral month M-1 and lag month L-1. The latter part of this equation is the completion factor. This slide demonstrates the basic approach to the completion factor method in spreadsheet form, although multiple variations on the theme exist. The incurred claims for each incurral month M and lag month L are arranged in the upper triangular claims completion matrix. Claim amounts in the upper left portion above the bold line are known claims which have been incurred and paid. Claim amounts to the lower right are point estimates of future unknown paid claims for each incurral month, i.e. the IBNR. The formula for cell A calculates the IBNR for that cell. Here, the amount of IBNR for claims incurred in March 2022 and expecting to be paid 4 months later in July, lag month 4, highlighted in red, would be equal to the amounts already paid for that incurral month in March, April, May, and June, lag months 0 through 3, highlighted in blue, times the sum of claims incurred in prior months and paid 4 months after the respective incurral months, highlighted in green, divided by the sum of claims incurred in prior months and paid within 3 months of the incurral, highlighted in yellow. The formula to calculate the IBNR amount for cell A is repeated for all unshaded cells in the lower right. Because the ratios are maintained by the formula, it does not matter that calculated IBNR cells may be included in the summations of the areas B, C, and D. The monthly IBNR subtotals reflect the sum of the IBNR cells for that incurral month. For March 2022, that amount is $558,349. The total IBNR is arrived at by summing the monthly IBNR subtotals in the IBNR row near the bottom, in this case $16.9 million. Total incurred claims are the sum of the cells in the total incurred row at the bottom. There are 2 major problems with the completion factor method. The first flaw is in the assumption that claims are paid at a constant rate, so that paid amounts in lag row L are positively correlated with the paid amounts for lag months 0 to L-1. As I will show in the following slides, this is a questionable assumption. Please note that the data presented here is from a mid-size HMO. Other results may vary. The graph shown on the left compares the PMPM paid amounts in the same month as a claim is incurred, that is lag month 0, with amounts paid in the first month following incurral, that is lag month 1, for the same incurral months. The graph on the right is similar, except that it shows the relationship of claims paid in lag month 1 to lag month 2. I also show the regression lines for the two sets of data, together with the coefficient of determination R² for both sets. R² is a goodness of fit measure for correlation, which reflects the amount of total variation explained by the model's regression lines. While there is no fixed method for determining the statistical significance of any given value of R², anything below 0.4 is generally considered to be a poor fit. As can be seen by the R² values shown here, the correlation of incurred amount from one lag month to the next in both data sets is weak at best. Indeed, the data actually shows a tendency towards negative correlations in both cases. Here are similar graphs showing the relationships between per member per month paid amounts in lag month 2 and lag month 3 in the left-hand graph, and between lag months 3 and 4 in the right-hand graph. In both cases, the coefficients of determination are essentially 0, hence no real relationship exists. Therefore, the assumptions of constant rate of payment and significant correlation between lag months are at the least questionable. The second problem with the completion factor approach is in the methodology itself. The completion factor method involves the multiplication of two random variables: the amount incurred and paid for each incurral month for any given lag period, and the completion factor itself. Multiplying random variables together greatly increases the method variance of the product. It is to be generally avoided if possible. This graph shows the relative monthly zero runout IBNR calculation errors using the completion factor method. The mean absolute error for the data is 24%, with individual monthly values ranging from -60% to +79%. The result of the combined flaws in the completion factor method is that the results are so unreliable that in practice the final IBNR requires 2 or 3 months of claims payment runout past the valuation date to get a usable result. This delay in reliable results is highly detrimental to their usefulness. Furthermore, there is no way in the completion factor method to directly determine confidence intervals around the point estimate. My conclusion is, in my opinion, the completion factor method is so deeply flawed as to have no real credibility with short runout. At first glance, the Bornhueter-Ferguson method appears completely distinct from the completion factor method. The Bornhueter-Ferguson method backs into the IBNR value by first projecting total incurred claims forward, then subtracting claims already paid. The first problem with the Bornhueter-Ferguson method is in determining the total incurred claims. These would presumably be obtained by evaluating past completed claims with longer runout periods, usually using the completion factor method, then projecting forward. By contrast to the completion factor method, the Bornhueter-Ferguson method assumes a negative correlation between claims already paid and claims yet to be paid. As shown by the data previously, this assumption is just as false as the assumption of positive correlation used by the completion factor method. In this next section, I will show a step-by-step example of the calculation of IBNR amounts using the average PMPM lag method. This example is only one version of the approach, with many variations possible to suit the available data and needs of the individual user. Some of the steps may be adapted or even omitted to simplify or to enhance the calculation. The average PMPM lag method operates by projecting past average PMPM claims for each lag period to the values of future unpaid claims for the respective lag periods, which are then summed. The average PMPM lag method does not assume a relationship between past paid claims for an incurral month and future unpaid claims for that month. Instead, they are assumed independent. The unpaid claims in the lag matrix are filled by averaging values across the matrix and then summing them together, so the variance of the results is kept to a minimum, since the sum of the cell variances is equal to the variance of the sum plus covariances in the case of correlated variables. Before I get into the details of the calculation itself, this slide shows the comparison of results of IBNR amounts calculated by the completion factor method versus the average PMPM lag method in relation to actual historical IBNR values for the data which I have used. The actual IBNR values are indicated by the green line. The scale on the left is omitted to protect the confidentiality of the data. The coefficient of variation, which is the standard deviation divided by the mean of the 42 data points, is 9.7%. The mean absolute error for the results obtained by the completion factor method, as indicated by the blue line, was 24%. The relative error values over 42 months ranged from minus 58% to plus 80%. The mean absolute error for the average PMPM lag method was 6.4%, as indicated by the red line, with error values ranging from minus 20% to plus 17% in January of 2023. So the average PMPM lag method is about 4 times as accurate as the completion factor method with no runout. The following slides present a detailed process for calculating IBNR for medical claims with no runout required for partial completion of the claims. The average PMPM lag method starts out very similar to the completion factor method by gathering the incurred and paid allowed claims by incurral month and lag month into the upper triangular claim lag completion matrix. While the process shown here starts out with allowed claims to be converted to paid claims in a later step, paid claims may also be used directly. So here is the initial claim lag matrix for this example, with calendar incurral months shown across the top and the claim payment lag months going down. Claims paid in the same calendar month as they were incurred are assigned lag 0. The data shown is based on actual claims data, but it has been transformed to protect confidentiality. The data covers a total of 36 months from July 2020 through June 2022, with the data from August 2020 to May 2021 not shown for the sake of space. This example is also based on the assumption that claims are essentially completely paid within 12 months. Next, past amounts are trended to the valuation date by multiplying by monthly trend factors. This example assumes a 6% annual trend. Error in the trend estimate will affect the final result to a small degree. For example, setting the trend estimate to 1% higher than actual will increase the final total IBNR estimate by about 1%, while underestimating the trend by minus 1% will cause the final total IBNR value to be lower by about 1%. The trend factors based on a 6% annual medical trend are shown across the top. The values from the prior slide are multiplied by these factors. For example, the allowed claims incurred in November 2021 and paid in April 2022, which is lag month 5, were $110,000. That amount was multiplied by 1.035 to bring it forward to the valuation date of June 30th, 2022 as $113,803. Step 3 involves applying medical cost seasonality to the trended amounts using historical seasonality data. The trended amounts are divided by the seasonality factors. If you are using allowed claims, then this adjustment will include only values for total medical cost, not including benefit seasonality due to annual deductibles, etc. If you use only paid claims in the analysis, then this adjustment will also include the effects of benefit seasonality and will obviate the necessity of applying benefit seasonality factors at step 8. Here, the seasonality factors are shown across the top. So for claims paid in November 2021 with 5 months of lag, the trended amount of $113,803 is divided by 0.997 to yield a seasonally adjusted value of $114,116. Step 4 uses the monthly covered member counts to convert the total adjusted allowed amounts from Step 3 to a per member per month basis. Simply divide the allowed claim amounts by incurred and lag months from Step 3 by the respective monthly member counts. So here, adjusted claims incurred in November 2021 and paid in lag month 5, $114,116, is divided by the 20,349 members in that incurral month to get a PMPM value of $5.61. At this point, the historical adjusted PMPM claim amounts are averaged by lag month. The average for each respective lag month is projected forward into the lower right IBNR section of the claims lag matrix. In this example, I have highlighted lag month 5 values for ease of interpretation. Notice that the average historic PMPM for lag month 5, $6.29 PMPM, is entered into each of the 5 incurred month columns to the right of the bold line. They should all have the same value. Steps 6 and 7 essentially reverse the adjustment processes from steps 2 and 3. Step 6 detrends the PMPM claim amounts by dividing all amounts in the matrix by the same trend factors that were used in step 2. So for April of 2022, the initially projected $6.29 PMPM is divided by 1.010 to yield $6.23 PMPM. The de-adjusted PMPM values to the right are no longer equal. Similarly, step 7 reverses the morbidity seasonality adjustments to the allowed claims by multiplying by the same calendar month seasonality factors as in step 3. Again, note that these seasonality factors do not include benefit seasonality, which will be addressed in step 8. So for claims incurred in April 2022 and expected to be paid in lag month 5, the $6.23 PMPM value from step 6 is multiplied by 0.894 to get $5.57 PMPM. Step 8 involves converting allowed claims estimates to paid claims by multiplying by the average paid to allowed ratios by calendar month. These ratios were developed from historical claim patterns by dividing the average monthly paid claims amounts by the average allowed claims amounts, then logarithmically smoothing them by calendar month. The benefit structure seasonality is implicitly included in the ratios. Typically, the presence of annual deductibles will cause the ratios for early calendar months, January and February, to be smaller. For April 2022, the historical smooth paid allowed ratio was 0.8455. So the estimate of PMPM claims to be paid in lag month 5 is $4.71. Finally, the PMPM values are converted back to total incurred and paid amounts by multiplying each column of numbers by the respective member totals for each incurral month. The total IBNR amount as of the valuation date is then arrived at by simply summing the projected values below the bold line to the lower right of the matrix. In this case, the estimated IBNR as of July 1, 2022, with zero claims payment runout is $11,957,214. If the user wishes to obtain IBNR amounts with some claims payment runout past a different valuation date, then simply omit summing the monthly cells to the right of the desired valuation date. For example, for a valuation date of May 1, 2022 with 2 months of payment runout, then the amounts in the columns for May and June are omitted, leaving an IBNR estimate of $1,795,231. One further advantage of this method is that future included claims can be estimated by projecting the PMPM amounts past the last paid date. For example, the estimate of paid claims in July 2022 just involves projecting claims by lag month one more month to the right. It is highly desirable to accompany point estimates of IBNR amounts with some measure of the uncertainty associated with those estimates. More traditional methods, such as the completion factor and Bornhueter-Ferguson methods, do not allow for the calculation of such measures. However, more recent stochastic simulation methods do include the ability to add uncertainty measures, such as confidence intervals. The average PMPM lag method allows for the direct calculation of confidence intervals associated with its IBNR point estimates. In this section, I will demonstrate the process for determining those confidence intervals. The calculation of confidence intervals using the average PMPM lag method starts out with the first 4 steps being the same as for the calculation of the point estimate, as demonstrated in the prior slides. Step 5 is where the calculations diverge. Instead of projecting average PMPM values for the lag month into the lower right portion of the matrix, the historical variances of the PMPM amounts by lag month are projected, as shown in Step 5a. Lag month 5 is again highlighted for illustrative purposes. The values in the green area to the upper left of the matrix represent the same PMPM adjusted allowed claim values as before. For each lag month, the variance of the values to the left of the bold diagonal line are projected to the incurral months to the right of the line for the respective lag months. So here, the variance of the PMPM costs for lag month 5 was $9.56. This value is entered into all of the 5 cells to the right of the bold line highlighted in red. The next step in the calculation of the confidence intervals is very similar to Step 6 for calculating the point estimate. For the calculation of the point estimate, the monthly PMPM values were divided by the appropriate trend factor from Step 2. For the calculation of the variance and confidence intervals, however, in Step 6a, the various PMPM variances are divided by the squared values of those respective trend factors. So note here that the lag month 5 variances are no longer the same. For example, for March, the detrended variance is equal to $9.56 divided by 1.015 squared equals $9.29. Likewise, Step 7a for the variance calculation is very like the corresponding Step 7 for the calculation of the point estimate. However, as in Step 6a, the respective PMPM variance values are multiplied by the squared values of the seasonal morbidity factors. So here, for example, the adjusted variance for lag month 5 of claims incurred in March is $9.29 times 0.939 squared, which is equal to $8.19. The next step is to sum the PMPM variances by incurral month to give total monthly PMPM variances. The formula for the variance of the summation of random variables is variance of x plus y equals variance of x plus variance of y plus 2 times the covariance of x and y. Because it was demonstrated previously that the correlation of values for lag time L and lag time L plus 1 is essentially 0, with r squared being less than 0.1, the covariance term can probably be safely omitted without a significant impact on the total monthly variances. Nevertheless, for form's sake, I will include the covariance terms in this example. The slide for step 8a shows the respective covariances for the successive lag periods L and L plus 1 towards the left side of the matrix. The formula for the total respective monthly variances is the sum of the variances by lag plus 2 times the sum of the covariances for the corresponding lag months. Here I put the covariance of the historic PMPM costs for the respective series of lag months L versus L plus 1 in a column on the left side of the matrix. Note that the covariances are mostly small and negative. For incurral month March 2022, the total variance is the sum of the variances shown in the March column plus 2 times the sum of the covariance values from lag month 5 to lag month 12, which is minus $1.34, giving a total monthly variance of $25.74. The monthly variances for the other incurred months are determined in a similar manner. Before the monthly PMPM variances are combined to get the total variance, the monthly variances are converted from an allowed basis to a paid basis by multiplying the individual monthly PMPM variances by the squares of the monthly paid allowed ratios from step 8 of the point calculation method shown previously. If the user is calculated based on paid claims from the beginning, then this step is not necessary. So in this example, the variance of total PMPM IBNR for March 2022 is $25.74 times 0.8298 squared, which is equal to $17.72. To get the total paid monthly variances, the monthly PMPM variances are multiplied by the squares of the numbers of members for the respective incurral months. So in this example, the total monthly variance for incurral month March 2022 is then $17.72 times 20,280 squared equals $7.29 times 10 to the 9th. In order to get the covariance values, I regress the monthly costs for the period from July 2020 through May 2022 against the costs of the same series set forward 1 month, that is from August 2020 through June 2022. In this example, the covariance was $3,937.24. The total variance is equal to the sum of the 12 total monthly variances plus 2 times 11 times this covariance, which is equal to 8.00 times 10 to the 11th. The standard deviation with 0 runout in the lower right is then equal to the square root of the variance, $894,560. The 95% confidence interval is plus or minus 1.96 times that amount, which equals plus or minus $1,753,337, or 14.7% of the point estimate. As with the calculation of point estimates for the IBNR, The variances for periods with non-zero claims payment runout involve simply dropping the variances and covariances of the incurred months after the chosen valuation date. For example, the variance for the point estimate on May 1, 2022 is the sum of the 10 prior variances plus 2 times 9 times $3,937.24, or $2.82 times 10 to the 10th. The 95% confidence interval for this estimate is then $1,795,231 plus or minus $329,367, or 18.4% of the IBNR point estimate. As a test of the variance methodology, I compared the calculated values for 36 consecutive confidence intervals against the actual IBNR amounts for the corresponding monthly valuation dates. As can be seen on this slide, on 34 of the 36 monthly points, the actual IBNR amount fell within the corresponding 95% confidence interval of the point estimate. This 94.4% accuracy rate is consistent with expectations. In conclusion, I would leave you with 3 points to consider. 1. Two traditional IBNR calculation methods, the completion factor and the Bornhueter-Ferguson, are shown to be seriously flawed. 2. The average PMPM Lag method avoids the flaws of these traditional methods and gives significantly more accurate estimates of IBNR. And 3. The average PMPM Lag method also allows for the direct calculation of statistical confidence intervals, further increasing the value of the methodology. The material presented here first appeared in the January, February, and May, June 2023 issues of Health Watch, a publication of the health section of the Society of Actuaries. It was also presented at the June 2023 health section meeting of the Society of Actuaries in Seattle, Washington. This methodology is in the public domain. Please feel free to contact me with any comments or questions. Thank you.